There was no sky, no silence, no darkness waiting beyond the edge because even space itself had only just begun. In the first fractions of a second after the Big Bang, the universe expanded, cooled, and started assembling the hidden foundations of everything we know. Quarks became protons, nuclei captured electrons, ancient light escaped the cosmic fog. Then, across an ocean of darkness, the first stars ignited and began forging the elements that would one day become planets, oceans, and the atoms inside us. This is not only the story of what happened after the Big Bang, it is the story of how the universe slowly became capable of remembering its own beginning. Thank you for spending part of your day or night with us. Tell us in the comments what time it is where you are and which part of the world you're listening from. If this journey brings you wonder, please like, subscribe, and share it with another curious mind. Now, let us return to the first light and follow the universe forward. The universe does not begin by throwing matter into a waiting darkness. There is no silent emptiness surrounding a central blast, no distant boundary racing outward, and no single place that can be called the point of origin. Instead, space itself expands. Every region of the early cosmos participates in the same transformation, so that the beginning is not somewhere inside the universe. It is the beginning of the universe as a physical stage at all. Time, distance, energy, and matter emerge together from a state so hot and dense that ordinary experience offers no useful comparison. The phrase Big Bang describes this expansion, but the word bang can be deceptive. It suggests sound, impact, and motion through pre-existing space. Modern cosmology describes something quieter and stranger. The fabric that defines separation begins stretching everywhere at once. Galaxies do not fly away from a central crater. Later, as space expands between them, they become more widely separated. Much as marks on a rising surface drift apart without any mark occupying a privileged center, this does not mean the entire universe was once a tiny ball sitting in a larger void. It means the observable universe was once compressed into an extremely hot, dense condition, while the full size or shape of the cosmos beyond what can be observed remains unknown. About 13.8 billion years ago, this condition begins to change. Expansion lowers the density and temperature. The universe does not cool because it releases heat into colder surroundings. There are no known surroundings. It cools because expanding space spreads energy through a growing volume and stretches the wavelengths of radiation. In this early state, familiar structures do not yet exist. There are no atoms, stars, planets, or stable chemical elements. Even protons and neutrons have not necessarily formed. Matter is not arranged into objects but exists as an intense field of particles, radiation, and forces interacting under conditions that cannot be reproduced in full. The earliest instant lies beyond the direct reach of telescopes because no light from that moment travels freely to the present. The universe is then opaque, energetic, and changing far more rapidly than at any later age. Yet the evidence for this hidden beginning survives in what expansion leaves behind. Distant galaxies show that space is still growing. Ancient radiation fills the sky. The proportions of the lightest elements carry traces of early nuclear reactions. Together, these clues reveal that the cosmos was once hotter, denser, and smoother than it is now. Following the story backward leads toward a limit where tested theories begin to lose their power. General relativity describes gravity and the large-scale behavior of space and time with remarkable success. But under extreme density, it points toward conditions where quantum effects must also matter. Quantum theory governs particles and fields at tiny scales, yet it does not fit completely with gravity. Near the beginning, both descriptions are needed at once, and no confirmed theory fully unites them. The earliest meaningful interval in current physics is often associated with the Planck era, a span so brief that its duration is difficult to express without scientific notation. In that domain, space and time may not behave as smooth backgrounds. They may fluctuate, emerge from deeper structures, or lose the ordinary meaning carried by words such as before and after. These possibilities remain speculative, not because science has abandoned evidence, but because the evidence is extraordinarily difficult to reach. The Big Bang model explains how the universe evolves from an early, hot, dense state. It does not yet provide a complete account of an absolute first cause. It also does not establish whether the cosmos begins from nothing, whether another phase precedes expansion, or whether time itself starts at the boundary described by the theory. Those questions sit close to the edge of current knowledge. Even the word beginning must be used carefully. In everyday life, every event follows an earlier event. A storm forms after changes in air pressure. A star forms after a cloud collapses. But if time is part of the universe rather than a container outside it, asking what happens before time may resemble asking what lies north of the northernmost point. The question may be meaningful in a deeper theory, or it may depend on an assumption that fails at the origin. Cosmologists therefore separate what observations support from what interpretation suggests. They can reconstruct much of the early evolution with increasing confidence. Yet the first boundary remains uncertain. One proposed bridge between the unknown origin and the observable universe is cosmic inflation. According to this idea, the young cosmos passes through an extremely brief phase of accelerated expansion. Space grows by an enormous factor, while the energy state driving inflation remains nearly uniform. This rapid stretching could explain why distant regions of the observable universe look so similar, even though, under a simpler expansion history, they would never have had enough time to exchange light or heat. Inflation could also explain why the geometry of the observable cosmos appears close to flat. Any initial curvature would be stretched across scales so vast that the visible region would seem nearly level, as a small patch of an immense sphere can appear flat. Inflation is not the same as the ordinary expansion continuing today. It is a proposed early phase governed by conditions that no longer dominate the universe, nor does it place a center inside space. Every region expands away from every other region because the distance scale itself changes. If inflation occurs, it may magnify a domain once microscopic into a region large enough to contain everything currently visible. This is where the first deep shift appears. The universe may begin in a condition that is nearly smooth, but it cannot be perfectly smooth. Quantum physics allows tiny fluctuations in fields and energy. During inflation, those fluctuations may be stretched from subatomic scales to astronomical ones. What begins as uncertainty in the smallest realm becomes a pattern spread across the cosmos. Some regions carry slightly more energy than others. After inflation ends and the universe fills with hot particles and radiation, those differences remain as faint variations in density. They are minute, but gravity is patient. Over hundreds of millions and then billions of years, slightly denser regions attract more matter, growing into the foundations of galaxies and clusters. The largest structures in the modern universe may therefore trace their ancestry to quantum variations formed when the cosmos was unimaginably young. The apparent emptiness of space, the arrangement of galaxies, and eventually the conditions that allow stars and planets may all descend from microscopic irregularities amplified by expansion. This possibility connects the smallest known scales with the largest. It suggests that the broad architecture of the night sky begins not with giant objects, but with subtle fluctuations almost too slight to describe. Inflation remains powerful because it links several observations within one framework, yet it is not directly witnessed. Scientists search for its fingerprints in the cosmic microwave background. The ancient radiation released much later when the universe becomes transparent. Certain patterns in that radiation could reveal how density fluctuations formed. A more elusive signal might come from primordial gravitational waves, ripples in space itself generated during the inflationary era. Detecting such a pattern would provide a rare view toward the hidden opening, but no definitive measurement has yet confirmed it. Different models of inflation also make different predictions, and some are harder to test than others. The theory may prove broadly correct, require revision, or be replaced by another explanation that produces similar evidence. For now, it stands as a carefully developed possibility rather than a finished chapter. Beyond it lie still wider ideas: bouncing universes, cyclic histories, quantum creation, and regions of space that continue inflating while local domains settle into calmer expansion. None is established. Their role is not to fill the darkness with certainty, but to mark the range of questions opened by the evidence. What follows the Big Bang therefore begins with an unusual mixture of confidence and mystery. Expansion is well supported. Cooling is well supported. The early hot state is written into radiation and elemental abundance. Yet the first instant, the cause of expansion, and the possible existence of an earlier phase remain unresolved. The universe enters history not as a completed place filled with objects, but as a changing geometry carrying energy, uncertainty, and the seeds of everything that later becomes visible. Before the first atom, before the first star, and before darkness itself can exist as a contrast to light, space is already stretching. Within that expansion, the future shape of the cosmos waits in differences so small that they seem almost absent, while the question of what truly begins remains hidden at the edge of time. The hidden first instant does not remain hidden because nothing happens there. It remains hidden because too much happens too quickly, under conditions where the usual language of space, time, and matter begins to fail. The universe has not yet settled into the familiar sequence of particles, atoms, stars, and galaxies. It exists in a state where energy dominates. Forces may not yet be distinct, and every interval of change is compressed into a scale far beyond ordinary intuition. Modern physics can follow the expansion backward with confidence for much of cosmic history. But the closer that reconstruction approaches the beginning, the more strongly it depends on theories that have not yet been fully tested. General relativity describes the geometry of space and time, while quantum theory describes the restless behavior of particles and fields. Each works with extraordinary accuracy in its own realm. Yet the earliest universe belongs to both realms at once. Gravity is intense enough to shape the whole cosmos, while quantum effects are strong enough to disturb even the fabric in which gravity operates. A complete account therefore requires a theory of quantum gravity, and no such theory has yet received decisive experimental confirmation. The result is not an empty gap, but a frontier filled with competing ideas. Some approaches treat space and time as fundamental. Others suggest they emerge from deeper relationships, as temperature emerges from the motion of countless molecules. Some imagine the earliest universe as a quantum state without a sharply defined history. Others propose that expansion begins after a prior contraction, replacing an absolute beginning with a cosmic rebound. These possibilities are not established facts. They show how difficult the first question becomes when the object being explained includes the origin of the clock used to describe it. The earliest interval that current theories identify is often called the Planck era. It ends after a fraction of a second so small that writing it in ordinary words gives little sense of its meaning. During this era, familiar measurements may lose their usual clarity. Distance may fluctuate. Time may not flow smoothly. The distinction between separate points in space may become uncertain. Even the idea of a single, well-defined geometry could be only an approximation that appears later, once the universe cools. No telescope can look directly into this interval. Light does not move freely through the early plasma, and any radiation from such conditions is repeatedly scattered and transformed. The evidence must therefore come indirectly, through patterns left in later cosmic structures. Inflation becomes important because it offers a way for those hidden patterns to survive. In many inflationary models, a field occupying space enters a high-energy condition. The energy of this field produces a powerful form of accelerated expansion. During an extremely short period, distances increase at a rate that causes a tiny region to swell into something vastly larger than the observable universe. This does not require objects to move through space faster than light. Relativity limits the local motion of matter and information, but space itself can expand so that distant regions separate faster than a beam of light could cross the growing distance. The same principle allows very remote galaxies in the modern universe to recede from one another at an effective rate greater than light without violating local physics. Inflation is often described as brief, but its significance comes from what it changes rather than how long it lasts. A region that begins in causal contact, able to exchange energy and approach a common temperature, can be stretched across the entire visible cosmos. This helps explain why the cosmic microwave background later appears almost equally warm in every direction. Without inflation, widely separated parts of the sky seem too distant to have reached such uniformity through ordinary communication. Inflation also dilutes unwanted relics that some high-energy theories predict, spreading them so thinly that they become nearly impossible to observe. It can flatten spatial curvature, making the visible universe appear geometrically close to flat, even if the full cosmos has a more complicated shape. These achievements make inflation attractive, but they do not reveal which version, if any, describes reality. The field that might drive inflation has not been directly identified. Its potential energy, its interactions, and the mechanism that ends the accelerated phase remain uncertain. The end of inflation introduces another transformation called reheating. Despite the name, the universe is not warmed from a cold state. Instead, energy stored in the inflationary field is converted into particles and radiation. The smooth, rapidly expanding domain becomes a hot cosmic mixture. The temperature rises to an enormous level, and the universe enters the more familiar hot Big Bang phase. This transition may generate the particles that later form matter, but its details depend on physics at energies far beyond present experiments. Reheating could happen quickly or through a more complex sequence. Fields may oscillate, decay, and transfer energy unevenly. Temporary particles may appear and vanish. Symmetries that hold at high energy may break as the universe cools, separating forces and giving different particles their properties. The most important surviving traces may begin as quantum fluctuations. A quantum field never becomes perfectly still. Even in its lowest energy state, it carries unavoidable uncertainty. During inflation, these microscopic variations are stretched beyond the scale where local processes can smooth them away. Once inflation ends, the fluctuations remain imprinted as slight differences in density and curvature. Regions with a little more energy eventually contain a little more matter. Regions with slightly less become comparatively empty. The contrasts are tiny, but they provide gravity with an uneven landscape. Much later, matter gathers into the denser regions, forming a web of galaxies and clusters separated by vast voids. In this way, quantum uncertainty may become cosmic geography. The connection is one of the most striking ideas in modern science, because it joins the smallest scales with the largest structures ever observed. It also means that the universe is not simply expanding from a perfectly smooth beginning. its future complexity is already present as a faint statistical pattern. Scientists test this picture by examining the cosmic microwave background and the distribution of galaxies. Inflation predicts that the early fluctuations should have a nearly scale-invariant spectrum, meaning that variations appear across many sizes with a particular balance. Observations broadly support this pattern. They also show that the fluctuations are close to Gaussian, with most variations small and extreme deviations rare. These agreements strengthen inflationary theory, but they do not select a single model. Many different inflationary scenarios can produce similar results. The clearest missing signal is a distinctive pattern of primordial gravitational waves. Inflation could generate ripples in space and time that leave a curled form of polarization in the cosmic microwave background. Experiments search for this pattern with sensitive instruments placed on satellites, high mountains, and polar ice. Dust within the Milky Way can imitate part of the signal, making the search difficult. So far, no detection has settled the question. The absence of a strong signal rules out some models but leaves many others alive. Inflation may occur at an energy too low to create a detectable imprint, or another process may explain the observed smoothness and structure. Alternatives include bouncing cosmologies, slowly contracting phases, and models in which fluctuations arise through different early universe mechanisms. Each must reproduce the same body of evidence: the uniform cosmic background, the near-flat geometry, the spectrum of density variations, and the later formation of structure. None has yet replaced inflation as the leading framework, but none of these questions is closed. Yet even without such wider speculation, inflation already changes the meaning of the beginning. The hot, dense state usually called the Big Bang may not be the absolute first moment. It may be the aftermath of an earlier inflationary phase, itself emerging from conditions still unknown. The first clear chapter of cosmic history could therefore begin not at the edge of existence, but after a hidden transition. What appears to be the opening may be a doorway whose far side remains inaccessible. The universe that follows carries evidence of this concealed era in its smoothness, its geometry, and the faint irregularities that later become galaxies. The first instant is absent from direct view, yet it may be written everywhere in the large-scale order of the cosmos. Every cluster, every void, and every future star may descend from a moment when space expands with extraordinary speed and quantum uncertainty is stretched into permanence. The beginning remains hidden, but it does not remain silent. Its traces wait in patterns spread across the sky, preserving a message from a time before matter has learned to take shape. The first durable pieces of matter emerge from a universe that is still far too hot for atoms, nuclei, or even protons and neutrons to remain intact. Expansion continues, and with it the temperature falls. But the cosmos is still filled with energies so extreme that familiar matter exists only as a possibility. Space contains a seething mixture of radiation and elementary particles, appearing, colliding, changing form, and disappearing again. At this stage, mass and energy move easily between one another. A collision can create particles, while a meeting between a particle and its antimatter counterpart can return their mass to radiation. Nothing resembles a solid object. There are no surfaces, no empty gaps between stable things, and no lasting structures larger than the brief interactions allowed by the temperature. The universe behaves less like a collection of objects than like a vast field of transformations. Among the most important participants are quarks and gluons. Quarks are elementary particles that later become the internal building blocks of protons and neutrons. Gluons carry the strong nuclear force, the interaction that binds quarks together. In the modern universe, quarks are never found freely under ordinary conditions. They remain confined inside composite particles. Yet in the earliest moments after inflation and reheating, the temperature is so high that this confinement has not fully taken hold. Quarks and gluons move through an exotic state known as quark-gluon plasma. It is not a gas in the ordinary sense, because its particles interact with remarkable intensity. Experiments suggest that such plasma can flow almost like a nearly perfect liquid, with very little internal resistance. For a brief period, this strange material may fill the entire observable universe. The strong force behaves differently at these energies. At very short distances, quarks interact more weakly, a property called asymptotic freedom. As the universe expands and cools, the effective strength of the force changes. Quarks can no longer wander independently across the plasma. They become confined in groups, most commonly in sets of 3, forming baryons such as protons and neutrons. Other combinations form particles called mesons, many of which are unstable and quickly decay. This transition does not create matter from nothing. It reorganizes existing energy and elementary particles into more durable forms. The cosmos begins to acquire a hierarchy. Elementary particles become composite particles. Composite particles later become nuclei. Nuclei eventually become atoms. At each stage, expansion lowers the temperature enough for a new kind of structure to survive. The process is gradual in cosmic terms, but extraordinarily rapid by human standards. Within the first tiny fraction of a second, the universe passes through physical conditions that never again fill all of space. The quark-gluon plasma leaves no direct light that travels unchanged into the present. Its properties must be reconstructed through theory, astronomical evidence, and experiments that briefly recreate similar states. At facilities such as the Large Hadron Collider, heavy atomic nuclei are accelerated to enormous speeds and smashed together. For an instant, the collision energy melts protons and neutrons into a droplet of quark-gluon plasma. This artificial fireball is microscopic and vanishes almost immediately, but the particles streaming from it carry information about how the plasma behaves. These experiments do not reproduce the Big Bang. They create only a tiny, short-lived sample under controlled conditions. Yet they offer one of the closest physical windows into the material state of the early cosmos. Measurements show that the plasma is strongly coupled, meaning that its components do not move as a simple cloud of independent particles. Instead, they influence one another so powerfully that the entire state flows collectively. This discovery changes the older picture of the early universe as a thin, chaotic particle gas. The primordial plasma is turbulent in its interactions, but surprisingly organized in its motion. Even before stable matter forms, the cosmos follows patterns that can be tested and measured. As cooling continues, protons and neutrons begin to survive. A proton contains 2 up quarks and 1 down quark, while a neutron contains 1 up quark and 2 down quarks. The difference appears small, but it has enormous consequences. Protons are slightly lighter and remain stable under ordinary conditions. Free neutrons are heavier and eventually decay unless they become bound inside atomic nuclei. In the early universe, however, energetic reactions repeatedly convert protons into neutrons and neutrons into protons. Their relative numbers are controlled by temperature and by the weak nuclear force. As long as the universe remains hot enough, these conversions continue rapidly and maintain a shifting balance. When expansion cools the cosmos further, the reactions slow. The ratio of neutrons to protons begins to freeze into place, preparing the conditions for the first nuclear elements that form minutes later. Yet this preparation depends on an even deeper mystery. The hot early universe should produce matter and antimatter in nearly equal amounts. Every quark has an antiquark counterpart. every electron has a positron. When these counterparts meet, they annihilate and release energy, usually as photons. The reverse can also happen when energetic radiation creates particle and antiparticle pairs. At sufficiently high temperatures, creation and annihilation remain in balance. As the universe cools, the energy available to create heavy pairs declines. Particles and antiparticles continue to meet, but fewer new pairs appear. Most should vanish into radiation. If the balance were exact, almost no ordinary matter would remain. The universe might still contain light and perhaps other forms of energy, but it would lack the material abundance needed for stars, planets, or living chemistry. Yet matter survives. For reasons not fully understood, the early cosmos contains a tiny excess of matter over antimatter. The imbalance may amount to only one additional matter particle among an enormous number of matched pairs. When the pairs annihilate, that small surplus remains. Everything later built from ordinary matter descends from this residue. Every galaxy, cloud, ocean, and cell exists because the cancellation is almost perfect but not complete. Physics requires a process capable of creating this asymmetry. Such a process must allow the number of matter particles to change, must distinguish in some way between matter and antimatter, and must occur outside complete thermal equilibrium. These broad conditions are known, but the exact mechanism is not. The established laws of particle physics contain differences between matter and antimatter, called violations of charge and parity symmetry. Yet the known effects appear too small to explain the cosmic imbalance. Additional particles, forces, or high-energy transitions may be involved. Some theories connect the asymmetry to the behavior of neutrinos, nearly massless particles that interact only weakly with ordinary matter. If heavy early forms of neutrinos once existed and decayed unevenly into matter and antimatter, they might create an imbalance in leptons that later becomes an imbalance in baryons. This idea, called leptogenesis, remains plausible but unconfirmed. Other models place the decisive event during transitions in the fields associated with fundamental forces. As the universe cools, symmetries break, much as cooling water changes into ice and selects a particular arrangement from many possibilities. A phase transition in the early cosmos could create regions, defects, or decays that favour matter slightly over antimatter. The details remain uncertain because the required energies lie beyond current particle accelerators. The surviving universe therefore carries evidence of a process that no experiment has yet directly revealed. Matter itself is the evidence. Its existence proves that something interrupts perfect symmetry, but it does not identify the cause. This mystery reaches beyond cosmology into the structure of physical law. Why should one form of matter endure while its mirror almost entirely disappears? Is the imbalance produced by known particles acting under extreme conditions? Or does it point toward physics not yet discovered? The answer may lie in rare particle decays, subtle neutrino behavior, hidden fields, or events that occur even earlier than the quark-gluon plasma. As the annihilations end, their energy floods the universe with radiation. Photons become vastly more numerous than surviving matter particles. This ancient ratio remains imprinted in the cosmos, where radiation carries the memory of countless vanished pairs, while matter represents the tiny remainder. The early fire does not simply cool into substance, it passes through a near erasure. Structure becomes possible because a minute imperfection survives that erasure. Protons and neutrons emerge from confined quarks. Electrons remain among the lighter particles, and neutrinos begin slipping through the plasma with increasing freedom. The universe is still only fractions of a second old, yet the essential inventory of ordinary matter is taking shape. No atom exists, and no chemical element has formed, but the pieces needed for both are now present. The primordial fire has begun to settle into persistence. From a state where particles appear and vanish almost without distinction, the cosmos develops survivors, and those survivors carry within them the unresolved reason that anything material remains at all. The universe survives its own near cancellation through a difference so small that it almost disappears inside the violence of the early cosmos. Matter and antimatter are created together, matched in mass and opposite in certain properties. A negatively charged electron has a positively charged counterpart called a positron. A proton has an antiproton. Quarks have antiquarks. When each particle meets its partner, both can vanish into radiation. In the opposite direction, sufficiently energetic radiation can produce a new pair. At the temperatures filling the young universe, these exchanges happen constantly. Matter becomes light, light becomes matter, and the distinction between substance and radiation remains fluid. If creation is perfectly balanced, then cooling should leave almost nothing behind. Each particle should find an antiparticle, and nearly all material content should dissolve into photons. Yet the universe does not become an empty sea of radiation. A minute excess of matter survives. That remainder becomes every atom later gathered into stars, planets, oceans, and living tissue. The imbalance is so slight that it can be described as a flaw in an almost perfect symmetry. But without that flaw, cosmic history ends before chemistry begins. The known universe therefore rests on a numerical difference that is tiny in proportion and enormous in consequence. Observations show that ordinary matter dominates the visible cosmos. Antimatter appears in certain reactions and laboratory collisions, but only in local, temporary quantities. There are no known nearby galaxies made entirely of antimatter. If large regions of matter and antimatter touched along cosmic boundaries, their interaction should produce intense patterns of high-energy radiation. Astronomers do not see the widespread glow expected from such annihilation zones. This absence suggests that the observable universe is not divided into neighbouring continents of matter and antimatter. The asymmetry appears to be built into the cosmic inventory itself. That conclusion deepens the mystery because the basic equations of particle physics often treat matter and antimatter with remarkable similarity. The distinction becomes dramatic only when matter and antimatter meet. Their mass converts into other particles and radiation, erasing both original forms. The early universe contains countless such encounters. Almost every particle present is removed in this way. The survivors are simply the unmatched excess left after the partners are exhausted. For every immense crowd of particle and antiparticle pairs, only a tiny surplus remains. That residue later appears abundant because the annihilations remove nearly everything else. The challenge is to explain how the excess forms before the cancellation ends. A successful explanation must satisfy several broad requirements. Physical processes must be able to change the number of baryons, the family of particles that includes protons and neutrons. Nature must distinguish matter from antimatter in at least some reactions. The universe must also pass through conditions away from complete thermal balance, because perfect equilibrium tends to erase any emerging difference. These requirements do not identify one mechanism, but they provide a framework for judging possible answers. The established theory of known particles, called the Standard Model, contains pieces of the necessary behaviour. Certain rare processes distinguish between matter and antimatter through a phenomenon known as charge and parity violation. For some interactions, performing both changes does not produce exactly the same result. The difference is real and measured. It appears in the behaviour of particles containing strange, bottom, and charm quarks. Yet the amount of violation observed in known reactions seems too weak to account for the cosmic surplus. The Standard Model may contribute, but it does not appear to tell the whole story. One possibility connects the imbalance to the electro-weak era, when electromagnetism and the weak nuclear force behave as aspects of a more unified interaction. As the universe cools, the symmetry between them breaks, and particles acquire their familiar properties through the Higgs field. If this transition occurs in a sufficiently abrupt way, expanding regions of the new state could create conditions far from equilibrium. Interactions near their boundaries might favour matter slightly over antimatter. This idea is known as electro-weak baryogenesis. It uses physics close to the known Standard Model, but the observed Higgs particle and current measurements make the simplest versions difficult to sustain. Additional particles or fields may be needed to strengthen the transition and provide more asymmetry. Experiments searching for new Higgs-like particles, electric dipole moments, or unusual decays may therefore test whether this path remains open. Another possibility begins with neutrinos. These elusive particles have no electric charge and interact so weakly that enormous numbers pass through stars, planets, and living bodies almost without disturbance. For many years they were thought to have no mass, but observations show that they change from one type into another, which means their masses are small but not zero. This discovery already proves that the simplest Standard Model is incomplete. Some theories propose heavy relatives of known neutrinos that exist only at extremely high energies in the early universe. Their decays may produce slightly different numbers of leptons and antileptons. Later processes could convert part of this lepton imbalance into the baryon imbalance carried by protons and neutrons. This mechanism, called leptogenesis, links the survival of ordinary matter to the hidden properties of neutrinos. It also raises the possibility that neutrinos are their own antiparticles. If so, a rare nuclear event called neutrinoless double beta decay may occur. Experiments search for this event deep underground, shielded from cosmic radiation. A confirmed detection would not prove leptogenesis by itself, but it would reveal that lepton number is not always conserved and would strengthen an important part of the idea. Other models place baryogenesis at still higher energies. Grand unified theories suggest that the strong force may once join with the electro-weak force. In such a regime, extremely massive particles could decay in ways that fail to preserve baryon number and slightly favour matter. These theories sometimes predict that protons are not perfectly stable. A proton might decay after an unimaginably long lifetime into lighter particles. No confirmed proton decay has appeared, placing strong limits on many models. The silence does not eliminate every grand unified possibility, but it narrows the range. The question of the matter surplus therefore reaches into experiments separated by scale and method. Particle colliders study rare decays and search for unknown fields. Neutrino observatories examine oscillations and possible differences between neutrinos and antineutrinos. Underground detectors wait for events that may occur less often than once across spans far longer than the present age of the universe. Astronomers search the sky for signs of primordial antimatter or unusual radiation. Each approach touches a different edge of the same ancient problem. No single result yet reveals the process that selects matter. The evidence is indirect because baryogenesis occurs under conditions that vanish almost as soon as they arise. The universe cools, the relevant particles decay, and the original asymmetry becomes locked into the surviving population. Once protons and neutrons form, the imbalance is no longer visible as an active process. It appears simply as the fact that matter exists. This makes the cosmos itself the final record of an event whose machinery has disappeared. The surviving abundance can be estimated by comparing ordinary matter with the sea of photons left from annihilation. There are vastly more photons than baryons, a ratio preserving how close the cancellation comes to completion. Matter is not the dominant remnant of the early particle age. Radiation is. The material universe is a thin residue within a much larger legacy of light. Yet gravity later gathers that residue into structures, making the rare component visually dramatic. Photons spread through expanding space, while matter clumps into clouds, stars, and galaxies. The universe looks richly material not because matter wins by a large margin, but because the tiny surviving fraction collects into luminous forms. The origin of that fraction remains one of the deepest links between particle physics and cosmology. It asks why symmetry is not exact, why the laws permit a preference, and why the preference points toward the matter that survives. The answer may come from a subtle extension of known physics, or from a hidden layer of particles and forces. It may emerge from neutrinos, phase transitions, unification, or a mechanism not yet imagined. Whatever the cause, the effect is already complete before the universe is old enough to form a single atomic nucleus. A nearly invisible bias passes forward through every later age. It enters hydrogen, burns in stars, becomes carbon and oxygen, and eventually forms systems able to investigate its origin. Cosmic structure grows from gravity, but the material available to gravity exists only because perfect balance fails. The early universe approaches emptiness through annihilation and stops just short. In that narrow remainder, all later complexity waits. The first atomic nuclei form in a universe that is only minutes old, yet the conditions that allow them to survive are already vanishing. Expansion continues to thin the primordial plasma, and the temperature falls from levels that break complex structures apart to levels where protons and neutrons can briefly remain joined. This interval is narrow. If the universe were cooling much faster, there would be too little time for nuclear reactions to build even the lightest elements. If it were cooling much more slowly, different reactions might continue long enough to produce a very different chemical beginning. Instead, the balance between temperature, density, and expansion creates a short furnace in which the first elements take shape. The process is called Big Bang nucleosynthesis. It does not produce atoms with electrons orbiting their nuclei. The universe remains far too hot for that. It produces only bare nuclei, immersed in radiation and surrounded by free electrons, neutrinos, protons, and other particles. Hydrogen begins in its simplest possible form, a single proton. Helium requires a more complicated assembly of protons and neutrons. Trace amounts of deuterium, helium-3, and lithium also emerge. Almost everything heavier must wait. The first obstacle is not a shortage of particles, but the overwhelming power of light. The young universe contains an immense number of energetic photons. Whenever a proton and neutron join to form deuterium, a fragile nucleus containing one proton and one neutron, a high-energy photon can strike it and tear it apart. Nuclear binding has begun, but the radiation field keeps reversing the work. This delay is known as the deuterium bottleneck, until the universe cools enough for destructive photons to become less effective. Larger nuclei cannot form in significant numbers because deuterium is the essential first step toward them. Protons and neutrons are present, but the bridge between individual particles and stable nuclei remains too fragile to cross. Meanwhile, free neutrons are unstable. Outside a nucleus, a neutron tends to decay into a proton, an electron, and an antineutrino. The longer nucleosynthesis is delayed, the fewer neutrons remain available. The final amount of helium therefore depends strongly on the timing. When deuterium finally begins to survive, nuclear reactions proceed rapidly. Deuterium nuclei collide with protons and neutrons, forming heavier forms of hydrogen and helium. These in turn combine into helium-4, a tightly bound nucleus containing 2 protons and 2 neutrons. Helium-4 is unusually stable, and once neutrons enter it, they are protected from free decay. Most of the surviving neutrons become locked inside helium. This leads to a simple but powerful outcome. The primordial universe ends nucleosynthesis with most of its ordinary matter in hydrogen nuclei and roughly a quarter of its nuclear mass in helium-4, along with very small traces of other light nuclei. The exact proportions depend on how many baryons exist, how quickly the universe expands, how long neutrons survive, and how the weak nuclear force behaves. Because these ingredients can be measured independently, primordial element abundances become one of the strongest tests of the hot Big Bang model. The success is not based on a vague resemblance. Nuclear physics predicts how reaction rates change with temperature and density. Cosmology predicts how rapidly the universe expands and cools. When these are combined, they produce expected abundances that broadly match observations. Hydrogen dominates. Helium appears in a substantial but smaller amount. Deuterium survives only as a rare trace because it is both difficult to form early and easy to consume once reactions accelerate. Lithium appears in still smaller quantities. Each element carries a different kind of information. Helium reflects the supply of neutrons and the overall timing. Deuterium is especially sensitive to the density of ordinary matter, because a denser plasma processes more of it into heavier nuclei. Lithium depends on several reaction pathways and remains more difficult to interpret. Astronomers seek the most ancient and least contaminated environments to compare these predictions with nature. Helium is measured in clouds of gas that contain very few heavy elements, because such regions have undergone less chemical processing inside stars. Deuterium is observed in distant gas lying along the paths to bright quasars, where its subtle absorption pattern can be separated from ordinary hydrogen. These measurements are difficult, but together they provide a view of the universe before the first star shines. They also reveal that nuclear synthesis is not merely a story about chemical origins. It is a probe of the early expansion rate and the number of light particle species present at the time. If unknown particles carried significant energy during these minutes, they could cause the universe to expand faster. That faster cooling would alter the neutron supply and shift the final element abundances. The light nuclei therefore place limits on forms of physics that may exist beyond the known particles. A trace of helium or deuterium becomes evidence about the total energy content of the cosmos during an era no telescope can directly observe. Neutrinos play an important role in this calculation. They interact weakly, but their energy contributes to cosmic expansion, and their behavior helps determine how protons and neutrons exchange identities before nuclear reactions begin. The agreement between predicted and observed light elements supports the broad picture of 3 known families of light neutrinos participating in the early universe. Any additional light species must fit within narrow limits, or avoid behaving like ordinary radiation during nucleosynthesis. In this way, the first nuclei become silent detectors of particles that may otherwise remain hidden. Yet the agreement is not perfect in every detail. The abundance of primordial lithium measured in some ancient stars appears lower than the simplest calculations predict. This mismatch is known as the cosmological lithium problem. It may reflect processes inside the stars that gradually destroy or hide lithium. It may result from difficulties in estimating their original composition. It could also point toward gaps in nuclear measurements or physics beyond the standard cosmological model. No single explanation has settled the issue. The discrepancy is small compared with the broad success of nucleosynthesis, but it remains persistent enough to matter. The simplest elements preserve both conformation and unease. The reason heavier nuclei do not form in abundance lies partly in the architecture of nuclear matter. There are no stable nuclei containing exactly 5 or exactly 8 nucleons that can serve as easy stepping stones. In stars, helium nuclei later overcome this difficulty through the triple alpha process, where 3 helium nuclei combine under sustained high temperature and density to form carbon. The early universe expands too quickly and has too low a density for this route to proceed efficiently. Its nuclear furnace shuts down before complex assembly can begin. Carbon, oxygen, silicon and iron are therefore absent except perhaps in quantities too tiny to shape later history. The Big Bang creates the basic fuel of future stars, not the full chemistry of planets or life. This limitation is as important as the elements that do form. The universe begins chemically simple because expansion interrupts nuclear construction. Once the temperature falls below the level needed for fusion, the composition freezes. Protons remain as hydrogen nuclei, helium nuclei drift beside them, deuterium and lithium persist as faint relics. For hundreds of thousands of years, these nuclei remain mixed with free electrons in a glowing plasma. No molecules exist. No solid grains form. No chemistry in the ordinary sense can begin. Yet the future is already divided into possibilities. Hydrogen will become the main fuel of stars. Helium will shape how those stars burn and evolve. Deuterium will remain a sensitive tracer of cosmic history. Lithium will carry an unresolved discrepancy from the first minutes into the oldest stellar populations. The heavier elements required for rock, water, air, and biology must be invented later within stellar cores and explosions. The early universe therefore provides not a finished material world but a sparse alphabet. Almost every visible structure will be written from hydrogen and helium, then revised by generations of stars. The first nuclei mark the moment when the cosmos begins preserving composition rather than merely exchanging particles. Their abundances are fixed before any light source appears, before gravity forms a galaxy, and before space becomes transparent. In a universe still glowing without stars, the first chemical memory settles into place. It is simple, incomplete, and remarkably precise, leaving later ages to transform a handful of light nuclei into the full material complexity of the cosmos. The first atomic nuclei drift through a universe that remains filled with light, but the light cannot travel freely. In practice, the cosmos behaves like a brilliant fog. Hydrogen and helium nuclei move through a sea of free electrons, while photons scatter again and again from the charged particles around them. A beam of light cannot cross a great distance without changing direction. There are no stars to illuminate darkness, because darkness, as a clear absence of light, has not yet formed. The entire universe glows. Every region is immersed in radiation left from the early fire, and that radiation remains tightly coupled to matter. The young cosmos is therefore both luminous and opaque, a vast plasma whose brightness cannot reveal what lies far away. Expansion slowly changes this condition. As space grows, radiation loses energy because its wavelengths stretch. The temperature falls, and the particles move with less violence. Yet for hundreds of thousands of years, the universe remains too hot for electrons to stay attached to nuclei. Whenever an electron is captured by a proton, an energetic photon soon arrives and tears the fragile atom apart. Hydrogen appears only briefly before returning to a charged state. Matter exists, but ordinary atoms do not survive. The turning point comes when the radiation field cools enough that destructive photons become rare. Electrons can then remain bound to nuclei, forming neutral atoms in large numbers. This transition is called recombination, although the name is slightly misleading because the particles are combining for the first time rather than returning to a previous atomic state. It unfolds when the universe is roughly 380,000 years old. The temperature has fallen to several thousand degrees, still hot by earthly standards but low enough for atomic structure to endure. Once electrons settle into hydrogen and helium, the number of free charge particles drops sharply. Photons no longer scatter at every step. The cosmic fog lifts. Light that has been trapped in the plasma begins travelling across space with little interruption. That released radiation still fills the universe today. Expansion has stretched its wavelengths by an enormous factor, shifting what was once visible and infrared light into the microwave region. Its temperature has fallen to only a few degrees above absolute zero. This ancient glow is known as the cosmic microwave background. It arrives from every direction, forming a faint layer behind galaxies, stars, and all nearer sources. It is not light from the first instant and not light from the Big Bang itself. It comes from the later moment when the universe becomes transparent. Before that time, repeated scattering erases any direct image of deeper history. The cosmic microwave background is therefore the oldest electromagnetic light that can move freely to modern instruments. It acts as a surface of last scattering, a distant boundary not located at one fixed place but surrounding every observer in every direction. The light seen from that surface begins its journey when photons last interact strongly with matter. Because the universe expands while they travel, the region releasing the light is now immensely far away. Observers in another galaxy would also see themselves surrounded by their own cosmic microwave background, formed from a different spherical region. There is no privileged center. The ancient light reflects the geometry of an expanding universe in which every location sees a horizon around itself. The discovery of this radiation transforms cosmology. A hot, early universe should leave behind a cooled background glow, while a universe with no hot, dense phase would struggle to explain such a nearly uniform signal. The radiation is first detected unexpectedly by radio astronomers who encounter a persistent microwave noise coming from the sky in every direction. Later measurements show that its spectrum matches the form expected from thermal radiation with extraordinary precision. This near-perfect spectrum reveals that matter and light once shared thermal equilibrium in a dense plasma. The cosmos has expanded and cooled, but the shape of the radiation field preserves the memory of that early balance. Satellites later map the background with increasing detail. The first measurements confirm its overall spectrum and reveal tiny variations across the sky. Subsequent missions sharpen the image until the differences in temperature can be traced across scales. These variations are extremely small, amounting to only slight deviations from the average. Yet they are not random blemishes. They record differences in density, motion, and gravitational potential in the young universe. Regions containing slightly more matter compress the plasma and influence the radiation escaping from them. Regions with slightly less matter leave different signatures. The cosmic microwave background becomes a map of the seeds from which later structure grows. Its mottled pattern is the early outline of the cosmic web. The physics behind the pattern begins before recombination. Ordinary matter and radiation are tightly coupled, while dark matter interacts mainly through gravity. Gravity tries to pull denser regions inward. Radiation pressure resists compression, pushing outward. The competition creates waves moving through the primordial plasma, similar in principle to sound waves, although no air is present. These acoustic oscillations rise and fall across regions of different sizes. When recombination frees the photons, the waves are caught at different phases. Some regions are compressed, others rarefied, and still others moving between those states. The background radiation preserves this frozen pattern. By measuring it, cosmologists can infer the proportions of ordinary matter, dark matter, radiation, and other cosmic components. The agreement between observation and theory is one of the central successes of modern cosmology. The universe appears close to spatially flat on the largest observable scales. Ordinary matter accounts for only a small fraction of the total cosmic content. Dark matter contributes much more mass, while a still larger share of the present energy budget is associated with dark energy. It also reveals the age of the universe, the rate of expansion under a chosen cosmological model, and the initial pattern of density fluctuations. Yet precision does not remove every mystery. Different measurements of the modern expansion rate do not perfectly agree, creating a tension that may reflect hidden errors or physics beyond the simplest model. Some large-scale features in the microwave sky appear unusual, though their meaning remains debated. The origin of the initial fluctuations still points back toward inflation, or another early mechanism not directly observed. The background gives a clear view of the universe as an infant, but it does not show what creates the infant state. Recombination also changes the role of ordinary matter. Before atoms form, radiation pressure strongly influences the charged plasma and prevents ordinary matter from collapsing freely into every gravitational well. Dark matter, unaffected by light in the same way, can begin gathering earlier. It forms invisible concentrations that help guide later structure. Once neutral atoms appear and photons decouple, ordinary gas is released from the grip of radiation. It can begin falling more effectively into the gravitational wells prepared by dark matter. This does not create stars immediately. The gas remains diffuse, and the universe enters a long period without luminous objects. But the essential barrier is gone. Light travels freely. Matter can clump more easily, and small differences in density can grow. The clearing of the fog therefore marks more than a change in visibility. It separates two cosmic eras. Before recombination, matter and radiation behave as a connected fluid. Afterward, photons stream across space while atoms respond increasingly to gravity. One universe becomes two intertwined histories, a bath of ancient light fading through expansion, and a field of matter slowly developing structure. The cosmic microwave background follows the first history, cooling and stretching without losing its basic pattern. Galaxies, stars, and planets follow the second, forming from the slight irregularities recorded within that pattern. Every microwave photon arriving at a detector has crossed nearly the entire history of visible space. It passes through growing galaxies, expanding voids, and changing gravitational fields before reaching the present. Some photons are scattered by later clouds of hot electrons, and others gain or lose small amounts of energy as cosmic structures evolve. These effects add further information, turning the background into a record not only of recombination but also of the universe through which the light travels. Still, beneath every alteration remains the original glow from the moment transparency begins. The universe is no longer a sealed furnace. It has become a place where distance can be seen. The first free light moves outward through a cosmos with no stars, carrying a pattern of almost invisible differences. Those differences are enough. Gravity will deepen them, dark matter will shape them, gas will fall into them, and the darkness ahead will eventually ignite. The lifted fog reveals no finished world, only a quiet foundation, neutral atoms, ancient radiation, and the faint unevenness from which all later structure will rise. The ancient light carries a pattern so faint that it almost disappears into uniformity. Across the cosmic microwave background, temperature changes from one region to another by only a tiny fraction. To ordinary sight, the early universe would seem nearly smooth. Yet gravity does not require large differences to begin its work. A region containing slightly more matter than its surroundings exerts a slightly stronger pull. That pull draws in additional material, deepening the contrast. A region with slightly less matter loses some of its contents to denser neighbours and becomes emptier. Over immense spans of time, these modest imbalances grow into the filaments, clusters, and voids that define the large-scale universe. The cosmic web begins as almost invisible texture in the primordial plasma. Its later grandeur is the patient result of gravity acting on an uneven beginning. After recombination, ordinary matter is no longer bound tightly to radiation. But the universe is still expanding rapidly. Expansion tends to separate matter, while gravity tries to gather it. Only regions with enough excess density can resist the general stretching and begin collapsing. Dark matter plays a central role because it starts forming gravitational wells earlier than ordinary gas. It does not scatter light, and it does not feel radiation pressure in the same way as charged matter. While photons push against the ordinary plasma before recombination, dark matter responds mainly to gravity. It gathers into loose concentrations, creating an invisible framework before atoms are free to fall into it. Once hydrogen and helium become neutral, ordinary gas streams toward these hidden wells. The visible universe begins assembling inside structures that remain unseen. Dark matter is still mysterious. Its presence is inferred through gravity rather than direct light. Galaxies rotate too quickly for visible matter alone to hold them together. Clusters bend background light more strongly than their stars and gas can explain. The pattern of structure also forms more efficiently when a large amount of unseen mass is present. Whatever dark matter is, it must interact weakly with light, and strongly enough through gravity to shape cosmic growth. Current evidence favours an unseen material component, but its identity remains unknown. Even so, its influence is written across the distribution of galaxies. The growth of structure does not proceed independently at every scale. The same early fluctuations that appear in the cosmic microwave background contain a range of sizes. Smaller variations can begin collapsing earlier, while larger regions take longer to gather enough matter. In many models, small dark matter halos form first. These halos merge into larger halos, which merge again. Gas falls into them, cools, and eventually forms stars. This pattern is called hierarchical growth. Large galaxies do not appear fully assembled. They are built through repeated combinations of smaller systems. The universe develops through accumulation rather than sudden design. As gravity draws matter inward, the arrangement does not become a random collection of isolated spheres. Collapse happens differently along different directions. A slightly denser region may contract first along one axis, forming a sheet. It may then contract along another, creating a filament. Where several filaments meet, matter gathers into dense knots. Between them, underdense regions expand and empty out. The result resembles an immense web stretching across hundreds of millions of light years. Galaxies line the filaments. Clusters occupy their intersections. Voids fill most of the volume between them. Their growth helps define the web just as strongly as the collapse of dense regions. Computer simulations make this architecture visible. Starting with a nearly smooth distribution of matter and a pattern of fluctuations based on observations of the early universe, simulations allow gravity and expansion to act over billions of years. The final result resembles the observed cosmic web with remarkable accuracy. This agreement links the ancient microwave pattern to the modern distribution of galaxies. It suggests that the universe does not need large initial structures. Tiny fluctuations, given enough time, are sufficient. The complexity of the present cosmos emerges from simple laws applied across enormous duration. Yet simulations also reveal how much remains uncertain. Gas does not merely fall quietly into dark matter halos. It heats as it compresses, collides with other streams, and cools by emitting radiation. The first stars inject energy and newly formed elements into their surroundings. Exploding stars disturb nearby gas. Growing black holes release powerful radiation and outflows. These processes can prevent gas from forming stars or drive it out of small galaxies. They can also trigger new collapse nearby. The visible structure of the universe therefore depends on both gravity and feedback, a continual exchange between gathering and expulsion. Dark matter establishes the broad framework, but ordinary matter fills that framework through complicated local events. The first galaxies likely begin in the densest regions of the web, where small halos merge and gas accumulates quickly. They are not calm spiral systems like the Milky Way. They are compact, irregular, and rich in unstable star formation. Their shapes change through collisions, tidal forces, and bursts of stellar birth. The line between a large star cluster and a tiny galaxy may be difficult to define. In the early universe, categories that seem distinct today are still forming. The cosmic web also guides the flow of gas. Filaments act as channels, feeding galaxies and clusters with material from surrounding space. Some gas enters gently in relatively cool streams. Some is heated to extreme temperatures when it falls into massive halos and strikes existing material. Within clusters, much of the ordinary matter does not reside in stars. It remains as hot, thin plasma spread between galaxies. On even larger scales, a significant fraction of ordinary matter may occupy warm and hot gas along filaments, faint enough to be difficult to detect. The web is therefore a structure of matter transport, carrying fuel toward growing stars and black holes. The pattern of the web preserves information about the early universe. The spacing of galaxies contains the lingering scale of the acoustic waves that once moved through the primordial plasma. This feature, known as the Baryon acoustic scale, acts like a standard ruler written into cosmic structure. By measuring its apparent size at different ages, astronomers trace how expansion changes over time. The same ancient waves that leave peaks in the cosmic microwave background later influence the preferred separation between galaxies. Gravitational lensing offers another view. As light from distant galaxies crosses the cosmic web, the gravity of intervening matter bends its path. The distortion is often weak, but when measured across large areas of sky, it reveals the projected distribution of mass, including dark matter. These maps show that visible galaxies sit within a broader invisible network. They also test how quickly structure grows, if gravity behaves differently on very large scales, or if dark energy changes the rate of expansion. The pattern of lensing may expose the difference. The web becomes a laboratory for physics that cannot be reproduced on Earth. Despite its vastness, the cosmic web remains connected to the smallest fluctuations of the early cosmos. A slight excess in density becomes a dark matter halo. Halos merge into a filament, gas enters the filament and feeds a galaxy. Stars ignite inside the galaxy and forge heavy elements. Planets later form from those elements. No new blueprint enters from outside. Structure grows because the universe begins almost smooth rather than perfectly smooth. The difference between those two conditions contains the entire future. The emptiest regions carry their own message. Voids expand faster than dense regions because they contain less matter to slow their growth. Galaxies near their edges are drawn toward filaments, leaving the interiors increasingly bare. Over time, small voids merge into larger ones, just as halos merge into larger structures. The universe becomes more contrasted. Dense regions grow denser, and empty regions become emptier. This contrast gives the cosmic web its delicate appearance. But the process is driven by gravitational sorting that unfolds for billions of years. By the time the first stars are ready to form, the universe already possesses an invisible geography. There are preferred places where gas can collapse, corridors through which matter flows, and vast regions that remain nearly empty. The architecture is still young, but its basic form is established. Gravity has begun translating primordial fluctuations into cosmic terrain. The microwave background preserves the original pattern, while galaxies reveal its mature expression. Between them lies the long, quiet work of structure formation, a process in which nearly imperceptible differences become the skeleton of the observable universe. After the cosmic fog lifts, the universe becomes transparent but not bright. The ancient microwave glow continues to fill space, yet it has already cooled beyond visible light, and no stars exist to replace it. The cosmos enters the long interval known as the cosmic dark ages. The name does not describe emptiness. Hydrogen and helium gas fills space, mixed with dark matter and fading radiation. What is absent is concentrated light. There are no stellar furnaces, no galaxies filled with luminous suns, and no heavy elements drifting through space. The universe can now be seen through, but there is almost nothing visible to see. This darkness lasts while gravity works in silence. The tiny density differences preserved in the cosmic microwave background continue to grow. Dark matter gathers first into halos, invisible regions whose gravity becomes strong enough to attract ordinary gas. These halos are small by later standards, but they provide the first shelters where collapse can begin. Gas flowing into them heats through compression. To form a star, the gas must lose that heat, or pressure resists gravity and halts the collapse. Cooling, therefore, becomes decisive. In the modern universe, gas often cools through radiation emitted by heavy elements or dust grains. None of those exist yet. The primordial gas contains almost only hydrogen and helium, both poor at radiating energy under many early conditions. A small amount of molecular hydrogen becomes essential. A molecule forms when two hydrogen atoms join. Though rare, these molecules can emit energy in ways that single hydrogen atoms cannot, allowing some primordial clouds to cool and contract. Their chemistry is simple, but their role is enormous. Without an effective path for losing heat, the first star-forming clouds would remain suspended inside their dark matter halos. The universe must invent a cooling mechanism before it can invent starlight. Molecular hydrogen does not form easily because the early universe contains little dust to help atoms meet. Instead, it develops through reactions involving free electrons and temporary negative hydrogen ions. These pathways produce only modest amounts, but in the densest regions that is enough. As gas collapses, the molecules radiate away part of the heat, allowing gravity to draw the cloud inward. The density rises. The central region becomes warmer again through compression, yet cooling prevents pressure from stopping the collapse too soon. A delicate contest unfolds between gravity, heat, chemistry, and the expanding background universe. The final outcome depends on the mass of the dark matter halo, the amount of molecular hydrogen, the surrounding radiation, and the speed at which material flows inward. Small changes can delay or accelerate the first stellar birth. This is why the exact timing remains uncertain. Some models allow the earlier stars to appear around 100 million years after the Big Bang, while others place widespread formation later. The broad sequence is clear, but the first ignition has not yet been observed with certainty. The Dark Ages are difficult to study precisely because they contain no bright objects. Ordinary telescopes detect light, and this era provides little of it. Astronomers therefore search for indirect signals. One of the most promising comes from neutral hydrogen itself. Hydrogen atoms can change the orientation of the electron and proton within them, producing or absorbing radiation with a wavelength of about 21 centimeters. Expansion stretches this signal to much longer wavelengths before it reaches the present. By mapping it across the sky and different frequencies, researchers hope to reconstruct hydrogen through the Dark Ages and the dawn of the first stars. The signal is extraordinarily faint and easily hidden by radio emission from the Milky Way, human technology, and the Earth's atmosphere. Even so, it offers a possible three-dimensional map of a period that remains almost completely invisible. Before the first stars appear, the neutral hydrogen should absorb some radiation from the cosmic microwave background under the right conditions. Later, the first luminous objects alter the gas, changing the pattern. Detecting these shifts would reveal when the cosmic darkness begins to end. It might also expose the influence of dark matter, unusual radiation, or other early physics. Several experiments search for the global average signal or for fluctuations across the sky. Claims remain difficult to confirm because the ancient signal lies beneath much louder nearby noise. The background universe continues cooling during this era. Radiation loses energy through expansion, while ordinary gas cools in a more complicated way. For a time, interactions with leftover free electrons keep the gas temperature linked to the cosmic microwave background. Later, the gas separates thermally from the radiation and cools faster as the universe expands. This makes neutral hydrogen especially sensitive to new heat. The first stars and black holes eventually warm it, but before then the gas remains cold and dark. The Dark Ages therefore preserve a relatively simple environment, though simplicity does not mean stillness. Matter moves along filaments, halos merge, gas shocks against itself, and chemistry slowly prepares the first collapse. Gravity deepens the invisible landscape established earlier. Some halos grow by drawing in diffuse material, others collide and combine. In their centers, gas densities increase until small regions become self-gravitating, meaning that the gravity of the gas itself begins to dominate over the larger halo. The collapse then accelerates. Fragmentation may divide a cloud into several dense cores, but primordial gas does not cool as efficiently as metal-rich gas in later galaxies. As a result, the first collapsing fragments may remain unusually massive. This helps explain why the earlier stars are expected to differ from most stars forming today. The absence of heavy elements changes not only chemistry but scale. A cloud that cannot cool to very low temperatures resists breaking into many small pieces. It may instead feed a limited number of large protostars. A protostar is a growing central object that has not yet begun stable nuclear fusion. Gas falls onto it through a rotating disk, increasing its mass and releasing heat. Radiation from the growing object pushes back against the infall, but under primordial conditions the accretion can remain intense. Magnetic fields may also develop, though their early origin and strength are uncertain. Jets and outflows could carry away angular momentum, helping material continue spiraling inward. None of this is directly visible yet. The first stellar embryos form inside dense cocoons of hydrogen, far beyond any current detailed image. Their existence is inferred from physical models and computer simulations. These simulations must follow gravity, gas motion, chemistry, radiation, and enormous differences in scale. A region spanning many light years can funnel matter into an object only slightly larger than a modern star. Different assumptions produce different stellar masses. Some first stars may become extremely massive, while others may form in smaller groups with more moderate masses. The old picture of a universe containing only solitary giant stars has softened into a wider range of possibilities. Yet most models still suggest that the first generation tends to be heavier than stars born in chemically enriched clouds. Darkness also changes the meaning of distance. Light from the cosmic microwave background crosses the universe, but it carries only the frozen pattern of recombination. No new beacon marks the growing halos. Vast structures assemble without announcing themselves. A region can become the future home of a galaxy, while remaining almost perfectly black. The Dark Ages are not an empty pause. They are the formative period in which the architecture of future light takes shape before light exists. The first stars depend on everything that comes earlier: the initial quantum fluctuations, the abundance of dark matter, the formation of neutral atoms, the chemistry of primordial gas, and the expansion rate of the universe. A change in any one of these could alter when and where ignition begins. The darkness is therefore a test of the entire cosmological story. When the first star finally turns on, the event is local and small compared with the universe, but its consequences spread outward. Nuclear fusion begins in a dense core, converting hydrogen into helium and releasing sustained radiation. Ultraviolet light enters the surrounding gas. Heat rises. Molecules break apart. Nearby material is pushed, compressed, and ionized. One point of light does not end the Dark Ages everywhere, but it changes the conditions around itself. Other stars soon appear in other halos. Their isolated bubbles of influence begin to multiply across the cosmic web. The universe approaches a threshold. For hundreds of millions of years, gravity has been gathering matter without visible reward. Now the first stellar furnaces are about to transform darkness into a new kind of history, one written not only in structure, but in light, heat, and the first elements heavier than lithium. The first stars do more than end the cosmic darkness. They change what the universe is made of. Before their birth, nearly all ordinary matter consists of hydrogen and helium, with only faint traces of lithium. The chemistry of space is simple, and every future element heavier than lithium still exists only as a possibility. When the earlier stellar cores begin fusion, that simplicity starts to break. The stars shine because gravity compresses their central gas until temperature and pressure become high enough for atomic nuclei to overcome their electrical repulsion and join. Hydrogen nuclei fuse into helium, releasing energy that pushes outward against collapse. A temporary balance forms between gravity pressing inward and radiation and hot gas pressing outward. This balance allows a star to live, but it is never permanent. The first generation, often called population 3 stars, is expected to form from pristine material containing no significant carbon, oxygen, iron, or dust. Without those heavy elements, the gas cools less efficiently and tends to collapse into larger fragments. Many early stars may therefore become far more massive than most stars forming in the modern universe. Some could contain dozens or even hundreds of times the mass of the Sun. Though the exact distribution remains uncertain, their great mass gives them fierce internal pressure, enormous luminosity, and short lives. A star with more fuel does not necessarily live longer, because its core burns that fuel much faster. The most massive first stars may survive only a few million years, a brief interval compared with cosmic history. Their light is intense and rich in ultraviolet radiation. Around each one, neutral hydrogen absorbs energetic photons and becomes ionized, splitting into protons and electrons. Molecular hydrogen, the coolant that helped the star form, is destroyed by ultraviolet light across nearby regions. This radiation can delay new star formation by removing an important cooling pathway, yet it can also compress gas at the edges of ionized bubbles and help trigger collapse elsewhere. From the beginning, starlight both suppresses and encourages creation. The earlier stars likely form in small groups rather than in complete isolation. Gas flowing through dark matter halos may feed several growing objects, and their radiation, winds, and gravity influence one another. Yet no telescope has clearly resolved a single population 3 star. Their existence is inferred from theory, from chemical patterns in ancient stars, and from the need for a first source of heavy elements. inside a massive primordial star. Fusion proceeds through a sequence of stages. Hydrogen becomes helium. When hydrogen in the core runs low, gravity compresses the center again, raising the temperature until helium nuclei can combine. Helium fusion produces carbon and oxygen in still more massive stars. Further stages create neon, magnesium, silicon, sulfur, and other nuclei. Each new fuel requires a hotter core because heavier nuclei repel one another more strongly. The process builds layers, with different forms of fusion occurring in nested shells around the center. The star becomes a furnace with an onion-like structure, though its interior is turbulent and constantly changing. This sequence cannot continue without limit. Fusion releases energy when light nuclei combine into more tightly bound nuclei, but the advantage diminishes as the products approach iron. Iron is among the most tightly bound nuclei. Fusing iron does not release useful energy, it consumes energy. Once an iron-rich core develops, the star loses the nuclear support that has resisted gravity. Collapse can begin with extraordinary speed. The core contracts, atomic nuclei are broken apart, and electrons are driven into protons, creating neutrons and neutrinos. A compact neutron-rich center forms, and the infalling outer layers strike it. The mechanism that turns collapse into explosion is complex, involving shock waves, turbulent flows, and a flood of neutrinos. When the explosion succeeds, a supernova tears through the star and ejects newly made elements into surrounding space. The first supernovae are chemical turning points. Carbon, oxygen, silicon, calcium, and iron are thrown into gas that previously contains almost none of them. Some heavier nuclei are produced during the explosion itself, when matter experiences intense flows of neutrons and extreme heat. Not every heavy element comes from the same event, and later sources such as neutron star mergers become important. But the first stellar deaths begin the enrichment of the universe. The material released by one star can travel across a small early galaxy, mixing unevenly with primordial gas. A later star may form from a cloud touched by only one explosion, preserving a chemical fingerprint of that single ancestor. Astronomers search for such fingerprints in very old, metal-poor stars in the Milky Way and nearby dwarf galaxies. In astronomy, metals are all elements heavier than helium. A star with extremely little iron may still contain unusual amounts of carbon or other elements. These patterns can reveal what kind of first star died before it. Some ancient stars appear enriched by explosions that release lighter elements while allowing much of the iron to fall back into a black hole. Others may preserve evidence of unusually energetic supernovae. Not all massive first stars die in the same way. Some collapse almost directly into black holes, ejecting little material. Their heavy elements remain trapped, and their deaths leave darkness rather than a bright explosion. Others explode as pair instability supernovae. In an extremely hot stellar core, energetic photons can transform into electron and positron pairs. This reduces the radiation pressure supporting the star, causing contraction and runaway nuclear burning. For a certain mass range, the resulting explosion can disrupt the entire star, leaving no neutron star or black hole behind. Such an event releases large quantities of heavy elements with a distinctive pattern. Astronomers continue searching for ancient stars that clearly preserve this signature, but the evidence remains uncertain. Stars above another mass range may collapse again because the explosion cannot overcome gravity, producing very massive black holes. These remnants may become seeds for the supermassive black holes found in later galactic centers. The rapid appearance of enormous black holes in the young universe poses a major puzzle. If they begin as remnants of massive stars, they must grow quickly by consuming gas and merging. Direct collapse of large gas clouds may provide heavier initial seeds. but the first stars could still contribute many early black holes. Their remnants gather within merging halos, sink toward galactic centers, and sometimes combine. The first stellar generation therefore shapes both chemistry and gravity. It enriches gas with new elements while leaving compact objects that influence future galaxies. Heavy elements transform the way later stars form. Carbon and oxygen allow gas to radiate energy more efficiently. Dust grains provide surfaces where molecules assemble and help shield cold regions from destructive light. Clouds can fragment into smaller pieces, producing stars with lower masses. Unlike the short-lived giants, small stars can survive for billions of years. Some may still exist today, carrying a diluted trace of the first enrichment. The transition from primordial stars to later populations is not instantaneous or uniform. Pristine pockets of gas may persist beside enriched regions. One halo can host a metal-free star while another nearby already forms a chemically richer generation. The early universe becomes a patchwork of different histories. Each explosion changes only a region, but mergers and gas flows gradually spread the products. Complexity advances through local events, not through one universal moment. The first stars also help drive cosmic reionization. Their ultraviolet radiation escapes into surrounding space and ionizes neutral hydrogen. Massive stars produce especially large quantities of energetic light, but their lives are brief, and dense gas can absorb much of their radiation. Small galaxies may allow a greater fraction to escape when supernovae clear channels through the gas. The combined effect of many early stars and galaxies creates expanding ionized bubbles that eventually overlap. The first stellar furnaces thus alter both matter inside galaxies and the transparency of the space between them. They turn a universe of hydrogen and helium into one capable of chemistry. They create the first substantial carbon, oxygen, silicon, and iron, then scatter those elements into clouds that later form new stars, planets, and living systems. Yet the first stars themselves remain mostly unseen, known through their consequences rather than their light. Their radiation fades into expansion, their explosions disperse, and many remnants sink into growing galaxies. What remains is an altered cosmos. The darkness does not simply end because light appears. It ends because stars begin changing the material future, forging complexity within their cores and releasing it through death. In the first stellar furnaces, destruction and creation become inseparable, and the universe begins the long chemical journey from simple gas to worlds. The first stars do not remain isolated sparks for long. They form inside small dark matter halos where gas is collected, and those halos continue to merge as the cosmic web grows. Each merger brings together stars, gas, black holes, and invisible matter, creating larger systems whose shapes change repeatedly. The earliest galaxies are therefore not calm, finished structures. They are compact, irregular, and unstable, brightened by bursts of star formation and disturbed by collisions. Their boundaries are uncertain because gas streams in from surrounding filaments, while radiation and supernovae push material back out. A galaxy at this stage is less a settled island than a changing region where matter is being gathered, heated, enriched, and rearranged. Through countless such regions, the universe begins to turn the scattered points of first light into a connected population of luminous structures. The same stars that brighten these galaxies also change the space between them. Ultraviolet photons leave stellar surfaces and travel into clouds of neutral hydrogen. When a photon carries enough energy, it removes the electron from a hydrogen atom, splitting the atom into a proton and a free electron. This process is ionization. Around each young galaxy, an expanding bubble of ionized gas begins to grow. At first, the bubbles are small and isolated, surrounded by a universe that remains mostly neutral. As more stars form and more galaxies appear, the bubbles enlarge. Some are driven by ordinary massive stars, while others may be strengthened by hot gas, stellar remnants, or feeding black holes. The exact contribution of each source remains uncertain, but together they begin a long transformation known as cosmic reionization. The name refers to hydrogen becoming ionized again after recombination allowed neutral atoms to form. Reionization does not happen everywhere at once. Dense regions containing many galaxies change first, while remote voids remain neutral longer. Ionized zones spread unevenly through the cosmic web, shaped by where sources form and how easily their radiation escapes. Gas close to a galaxy can absorb most of its ultraviolet light, especially when the galaxy is rich in dense clouds. Supernova explosions may clear channels through that gas, allowing more radiation to reach intergalactic space. Small galaxies may be particularly important because they are numerous, though each one is faint. Larger galaxies produce more light but can also trap much of it. The balance between abundance, brightness, and escape remains one of the central questions in the study of the early universe. Reionization changes the thermal state of intergalactic gas. When neutral hydrogen absorbs energetic photons, part of the energy becomes heat. The gas warms, pressure rises, and small halos find it harder to capture fresh material. In some regions, the first generations of galaxies therefore alter the conditions for later galaxies. Their light can suppress star formation in the smallest halos, even as it clears the fog that once hid them. Cosmic history becomes increasingly self-regulating. Stars create radiation. Radiation heats gas. Hot gas changes collapse, and change collapse determines where the next stars appear. The universe is no longer evolving only under gravity. Light itself has become a force-shaping structure. Observations of this period are difficult because the signals arrive from extreme distance and have been stretched by expansion. Galaxies from the reionization era appear faint and red, and the neutral hydrogen around them absorbs much of their ultraviolet light. Astronomers identify candidates through characteristic breaks in their spectra, where radiation disappears below wavelengths absorbed by hydrogen. The James Webb Space Telescope extends this search deeper into cosmic history, revealing unexpectedly bright galaxies at very early times. Some appear to contain more stars, dust, or chemical enrichment than simple models once anticipated. These findings do not overturn the broad framework of galaxy formation, but they challenge researchers to explain how gas cools, stars form, and black holes grow so efficiently in young systems. Early galaxies may convert gas into stars in short, intense bursts. They may be magnified by gravitational lensing. Their light may be dominated by unusual stellar populations or active black holes. Precise interpretation remains difficult because a small, distant source can hide several physical processes within one point of light. Galaxies grow through two related paths. They draw in fresh gas from the cosmic web, and they merge with other galaxies. Gas accretion supplies the raw material for new stars. Mergers rearrange existing stars and can compress gas, triggering rapid star formation. Small mergers occur frequently as tiny systems combine. Larger collisions become less common but more dramatic. The shapes of galaxies respond to these encounters. Rotating disks can be disturbed, thickened, or torn into tidal streams. Central concentrations of stars can grow. Gas can lose angular momentum and fall inward, feeding dense starbursts or black holes. Yet mergers are not simply destructive. They assemble larger galaxies, mix chemical elements, and create new structures from the remnants of older ones. The Milky Way itself carries evidence of this process in streams of stars and in populations with different motions and compositions. Its present form is the temporary outcome of a long merger history that begins in the earliest cosmic web. Black holes grow alongside galaxies. Some begin as remnants of massive stars. Others may form through the direct collapse of large gas clouds, producing heavier seeds. Once a black hole sits within a gas-rich system, it can gain mass by accretion. Gas spiraling inward heats through friction and compression, releasing enormous amounts of radiation before crossing the event horizon. A feeding supermassive black hole can outshine the stars of its host galaxy and appear as a quasar. Quasars are visible from a time when the universe is still young, which means some black holes reach billions of times the mass of the Sun with surprising speed. Their growth requires favourable conditions, abundant gas, sustained inflow, mergers, and perhaps massive initial seeds. The details remain uncertain. Accretion may exceed simple limits for brief periods, or obscured phases of rapid growth may hide much of the process. Black hole mergers also add mass, especially as their host galaxies combine. The energy released by active black holes does not remain confined to the center. Radiation, winds, and jets can heat surrounding gas or drive it out of the galaxy. This feedback may slow star formation by removing fuel, but it can also compress clouds and encourage new collapse. Over time, black hole activity helps connect the fate of a tiny central region with the evolution of an entire galaxy. The close relationship observed between the masses of central black holes and the properties of their host galaxies suggests that they grow together, though the direction of cause and effect is still debated. In the early universe, the connection is forming amid repeated inflow and collision. As ionized bubbles spread, they begin to overlap. Neutral islands shrink between them. Light travels farther without being absorbed, and the intergalactic medium becomes mostly ionized. This marks the end of reionization, though small pockets of neutral gas remain inside dense systems and self-shielded clouds. By roughly the first billion years of cosmic history, much of the hydrogen between galaxies has undergone this transformation. The exact timeline is still being refined through observations of distant quasars. Galaxies, the cosmic microwave background, and the faint 21-centimeter signal from neutral hydrogen. Each method provides a different view. Quasar spectra reveal absorption by intervening gas. The microwave background records scattering by free electrons. Galaxy surveys estimate the amount of ultraviolet radiation produced. Radio experiments seek the disappearing neutral medium directly. Together they describe a transition that is gradual, patchy, and closely tied to the first generations of luminous objects. By the time reionization is largely complete, the universe has changed in several fundamental ways. It contains galaxies rather than isolated first stars, heavy elements rather than only primordial gas, and grow in black holes capable of influencing vast regions. The cosmic web is now illuminated along its densest threads. Filaments feed galaxies, galaxies merge, stars enrich their surroundings, and black holes regulate the flow of gas. None of these systems is permanent. A galaxy can brighten, fade, collide, lose material, and begin again. The universe builds complexity through repeated disturbance. Its order is not stillness, but a pattern maintained through motion. The darkness after recombination ends not in a single sunrise, but in millions of expanding bubbles, scattered starbursts, and merging halos. Gradually, the bubbles join, the galaxies grow, and light finds longer paths through space. The young cosmos awakens through fragmentation and reunion, assembling luminous structures from pieces that are continually broken, combined, and transformed. Long after the first stars begin enriching space, the universe contains enough chemical variety for a different kind of structure to form: carbon, oxygen, silicon, magnesium, sulfur, Iron and other elements drift through galaxies as gas and dust, mixed with the hydrogen and helium left from the beginning. These heavier atoms do not spread evenly. They collect in clouds shaped by earlier generations of stars, supernova explosions, stellar winds, and galactic motion. Within one such region of the Milky Way, more than 9 billion years after the Big Bang, a new stellar system begins to take shape. The cloud is not pristine. It carries the chemical memory of many vanished stars. Some of its atoms were forged quietly in stellar cores. Others were created during violent explosions or in collisions involving compact remnants. Gravity draws part of the cloud inward. As it contracts, small irregularities grow. The densest center accumulates most of the mass, while the rest flattens into a rotating disk because angular momentum prevents everything from falling directly inward. Compression heats the central region until hydrogen fusion begins. The sun is born. Around it, the disk remains filled with gas, ice, dust, and solid grains. These grains collide, stick, fragment, and collide again. Electrostatic forces help the smallest particles cling together. As clumps grow, gravity becomes more important. Pebble-sized bodies become larger aggregates, and aggregates become planetesimals, solid objects large enough for their own gravity to shape further growth. Some collisions build, while others destroy. Over time, a limited number of larger objects dominate their regions and sweep up surrounding material. The inner disk is too warm for many volatile substances to freeze, so the worlds forming there are built mainly from rock and metal. Farther out, water, methane, ammonia, and other compounds condense as ice, allowing planetary cores to grow rapidly and capture thick envelopes of gas. Earth forms within the warmer inner region. Its earlier state bears little resemblance to the later blue planet. Accretion releases enormous heat. Radioactive elements add more. Dense iron sinks toward the center, while lighter silicate rock rises above it, separating the planet into core, mantle, and crust. Large impacts repeatedly melt parts of the surface. One collision, likely involving a body roughly the size of a small planet, sends material into orbit that later gathers into the moon. Water and other volatile materials arrive through several pathways. Some are present in Earth's original building blocks. Additional amounts may come from water-rich asteroids, while comets may also contribute. As the surface cools, water vapor condenses and oceans become possible. Volcanic gases build an atmosphere unlike the modern one. There is little free oxygen, carbon dioxide, nitrogen, water vapor, and other gases dominate, while impacts and eruptions continue to reshape the surface. Every major ingredient has a deeper cosmic origin. Hydrogen comes largely from the early universe. Carbon is built in stars through the fusion of helium. Oxygen forms in massive stars and spreads through stellar winds and explosions. Silicon and magnesium arise in later fusion stages. Iron is assembled near the end of massive stellar lives and released when some of those stars die. Calcium, phosphorus, and many rarer elements require additional nuclear pathways, including explosive events and collisions involving neutron stars. The materials of Earth are products of different cosmic environments, brought together inside one planetary system. The iron in the planet's core and in living blood shares a history reaching into stellar furnaces. The calcium in rock and bone descends from nuclear reactions completed before the sun exists. The oxygen in oceans and air is the residue of stars that vanish long before Earth forms. Gravity and chemistry unite this inherited matter into one evolving world. Once a stable crust and persistent oceans emerge, chemistry begins exploring combinations that stars cannot produce. In space, atoms are forged. On planets, Those atoms are rearranged into minerals, molecules, and eventually systems capable of replication and metabolism. The path from chemistry to life remains uncertain. No complete record survives from the earlier stages, and no laboratory has recreated the full transition from simple compounds to the first living system. Yet the broad requirements are known. Life depends on energy, environments where molecules can concentrate and interact, and materials capable of storing information while changing over generations. Early Earth provides many possible settings, including volcanic pools, mineral surfaces, hydrothermal systems beneath the ocean, and regions shaped by repeated drying and wetting. Different processes may cooperate rather than compete. Simple organic molecules can form through atmospheric chemistry, reactions around hydrothermal vents, and delivery by meteorites. Some meteorites contain amino acids and other carbon-rich compounds, showing that prebiotic chemistry is not limited to planets with life, yet ingredients alone do not explain organization. Molecules must become linked into networks that persist, copy, and evolve. At some point, chemistry begins producing variation that natural selection can preserve. That threshold may occur only once on Earth, or many times, with one lineage surviving. Its timing remains uncertain, but evidence suggests that life appears relatively early once stable environments exist. The first organisms are simple and microscopic. They transform the planet not through size but through metabolism. Some use chemical gradients near the seafloor, others capture energy from sunlight. Over immense time, biological activity alters oceans, rocks, and atmosphere. Photosynthetic organisms eventually release oxygen as a waste product. At first, much of it reacts with iron and other materials. Later, it begins accumulating in the atmosphere, changing planetary chemistry and making new forms of life possible. Earth does not merely host life. Life becomes part of Earth's geology. It changes mineral diversity, atmospheric composition, and the cycling of carbon, nitrogen, sulfur, and other elements. The planet and its organisms evolve together. This remains part of cosmic history because every biological process depends on stellar material and planetary conditions established long before life begins. The energy driving most surface ecosystems comes from the sun. The atoms carrying that energy through cells come from previous stars. Even the planet's orbit, liquid water, atmosphere, and internal heat emerge from the earlier assembly of the solar system. Life is not separate from cosmology. It is one of the later ways matter behaves when expansion, gravity, fusion, chemistry, and time combine under favorable conditions. Consciousness appears much later, after billions of years of biological evolution. Nervous systems grow more complex. Sensory information becomes integrated. Memory allows experience to influence future behavior. Eventually, within one species, matter develops the capacity to reconstruct events that occur before Earth, before the sun, and before any star shines. Instruments detect the cosmic microwave background. Telescopes measure distant galaxies. Particle experiments recreate droplets of primordial plasma. The universe begins examining its own history through structures built from ancient atoms. This does not make human life central to the cosmos. It makes it continuous with the cosmos. There is no boundary where cosmic evolution ends and earthly existence begins. The same story changes scale. Quantum fluctuations become galaxies. Galaxies produce stars. Stars produce heavy elements. Heavy elements become planets. Planetary chemistry becomes life, and life becomes awareness. Each stage depends on the earlier one without being fully predictable from it. Complexity appears through new relationships among old materials. The dust that forms Earth does not know that it will become ocean, bone, forest, or thought. Yet the possibility is present in the laws governing how matter can combine. The solar system is one local outcome among countless systems formed across the universe. Many stars possess planets, and some may contain conditions suitable for chemistry similar to Earth's. Whether life appears elsewhere remains unknown. The same elements are widespread, and the same physical laws operate throughout the observable cosmos. But the emergence of life may depend on rare sequences not yet measured. Earth proves that cosmic matter can become living and reflective. Not that it commonly does. From the perspective of deep time, observers are recent and fragile. Yet the atoms within them carry nearly the entire earlier story. Hydrogen preserves the beginning. Carbon and oxygen preserve stellar interiors. Iron preserves stellar death. The planet preserves collisions, cooling, and chemical change. Life preserves a continuous line of replication reaching into Earth's ancient past. The body becomes a meeting place of cosmic ages. Stardust is not merely a poetic description. It is a physical inheritance. Material once scattered through dark interstellar space becomes part of a world where the universe can form questions about its own origin. The journey after the Big Bang therefore moves not only outward into larger structures, but inward toward finer organization. Expansion creates room. Gravity gathers matter. Stars forge complexity. Planets concentrate it. Life gives it continuity. Mind gives it memory. The universe that begins without atoms eventually contains beings capable of tracing those atoms back through fire, darkness, and time. The universe does not stop changing when stars, planets, and living worlds appear. Expansion continues through every later age, and the future depends on a force whose nature remains unknown. Observations show that distant galaxies are receding from one another, not because they are moving through a fixed emptiness, but because the space between them is growing. More surprisingly, this expansion is accelerating. Gravity should slow the separation by pulling matter together, yet on the largest scales another effect dominates. Cosmologists use the name dark energy for the unknown component associated with this acceleration. The name describes a role, not an explanation. It may be a constant energy woven into empty space, a changing field, or a sign that gravity behaves differently across immense distances. Current measurements indicate that it outweighs both ordinary matter and dark matter in the present cosmic budget. But its physical identity remains hidden. That ignorance makes the distant future uncertain. Even though several broad possibilities can be traced, if dark energy remains nearly constant, the universe continues expanding forever. Galaxies that are not gravitationally bound to one another recede more rapidly as space grows between them. Their light becomes increasingly stretched and faint. Over enough time, many cross a cosmic horizon beyond which no future signal can ever reach the Milky Way. The expansion simply carries them into regions that become permanently disconnected from local observation. A future observer inside the merged remains of the Milky Way, and Andromeda may see far fewer external galaxies than are visible now. The cosmic web will still exist beyond the horizon, but its light will no longer arrive. The observable universe becomes emptier, not because structure disappears everywhere, but because expansion hides it. Within gravitationally bound groups, another history continues. The Milky Way and Andromeda are moving toward one another and are expected to merge after several billion years. Their stars are separated by such large distances that direct stellar collisions remain unlikely, but their gravitational structures will interpenetrate and rearrange. Gas clouds may compress, producing new periods of star formation. The central black holes may eventually merge, releasing gravitational waves through the remnant galaxy. Over time, the combined system relaxes into a larger, smoother collection of stars. Beyond this island of gravity, accelerated expansion carries distant systems away. Stars continue shining, but not forever. Their light comes from finite nuclear fuel. Massive stars burn quickly and die first, leaving neutron stars or black holes, while stars like the Sun survive for billions of years before becoming white dwarfs. The smallest red dwarfs are far more patient. They consume hydrogen slowly and may shine for trillions of years. Their long lives extend the stellar era far beyond the present age, but even they eventually exhaust their usable fuel. Star formation also declines. Galaxies turn much of their cold gas into stars, heat it, or expel it into surrounding space. Collisions between galaxies can briefly renew stellar birth, yet the overall supply diminishes. The universe enters an age in which new stars become rare and old stars dominate the remaining light. As the final red dwarfs fade, the cosmos is populated increasingly by stellar remnants. White dwarfs cool slowly after losing the outer layers of sun-like stars. Neutron stars remain as dense cores left by supernovae. Black holes persist where the most massive stars collapse or compact objects merge. Brown dwarfs, failed stars too small to sustain ordinary hydrogen fusion, drift through darkened galaxies. Planets and smaller bodies continue orbiting remnants or wander freely after gravitational encounters eject them. Binary remnants still merge. Rare encounters may ignite brief flashes long after normal star formation has ceased. In dense stellar systems, gravity gradually rearranges the remaining bodies. Some fall towards central black holes, while others gain energy and escape into intergalactic space. Over immense spans, galaxies can evaporate through repeated gravitational encounters, losing stars and remnants one by one. What remains may be a central black hole surrounded by an increasingly sparse cloud of dark objects. Matter itself may not be eternal. Some theories predict that protons eventually decay into lighter particles, though no such event has been observed. Experiments show that protons survive for at least extraordinarily long periods, but they cannot yet prove absolute stability. If proton decay occurs, planets, white dwarfs, and other ordinary matter gradually dissolve into radiation and lighter particles. If protons are perfectly stable, remnants may persist much longer, though rare interactions could still transform them. The future therefore depends not only on dark energy, but on particle properties that remain unknown. Black holes appear almost permanent on ordinary timescales, yet quantum theory predicts that they slowly lose energy. Near an event horizon, quantum fields allow radiation to escape, causing the black hole to shrink. This process is known as Hawking radiation. For stellar and supermassive black holes, the effect is unimaginably weak in the present universe because surrounding radiation is warmer than the radiation they emit. Far in the future, as the cosmic background cools, black holes begin losing more energy than they absorb. Small ones disappear first. The largest black holes endure for spans vastly longer than the stellar era, but even they eventually evaporate if the theory is correct. Their final stages release a brief increase in radiation before the horizon vanishes. After the last black hole fades, the universe may contain mostly low-energy photons, neutrinos, electrons, positrons, and other stable particles spread through an enormous volume. Expansion continues to dilute them. Temperature differences flatten. Concentrated sources of usable energy become rare. This projected condition is often called heat death. The phrase does not mean that the universe becomes hot. It means that energy approaches a state of broad equilibrium, leaving little ability to perform work or sustain complex change. Events may still occur, but they become increasingly isolated and insignificant. Time continues, Yet fewer processes mark its passage. The cosmos does not end with a final explosion. It thins, cools, and fades towards stillness. This future follows if dark energy behaves like a constant. Other possibilities remain open. If dark energy strengthens with time, accelerated expansion could become increasingly violent in a hypothetical Big Rip. The stretching of space eventually overcomes the forces holding structures together. Galaxy clusters separate, then galaxies, then planetary systems, and perhaps matter itself. The exact sequence depends on how rapidly the repulsive effect grows. No evidence currently requires such an outcome, but it cannot be dismissed without understanding dark energy more deeply. A different possibility emerges if dark energy weakens, changes sign, or proves temporary. Expansion could slow. In some models, gravity eventually reverses it, drawing galaxies together into a contracting universe. A big crunch would compress structure, heat radiation, and carry the cosmos toward another dense state. Some speculative theories imagine that such a collapse could lead to a bounce and a new expansion, but no observation confirms this cycle. Another uncertain path arises from quantum fields. Empty space may occupy a state that appears stable but is not the lowest possible energy. A transition to a lower state could spread through the cosmos and alter the properties of particles and forces. The possibility remains speculative because the true structure of the vacuum is unknown. These possible endings reveal how much the future is connected to questions first posed near the beginning. Inflation may depend on vacuum energy. Dark energy may also arise from the nature of empty space. The imbalance between matter and antimatter determines what survives into the stellar era. Proton stability determines whether matter endures after stars fade. Quantum gravity may shape both the origin and the ultimate fate of black holes. The universe begins in conditions beyond current theory and may end in conditions equally remote from experiment. Between those limits lies a brief luminous age in which galaxies shine, elements circulate, planets form, and life becomes possible. The present exists within that interval. The cosmos is old enough for many generations of stars to enrich space, yet young enough that starlight still fills the sky. Most stars that will ever exist may already have formed, but the future remains incomparably longer than the past. The universe after the Big Bang is therefore not a completed story moving toward one certain conclusion. It is an unfolding history whose final direction depends on forces and particles still unexplained. Expansion carries galaxies apart. Gravity builds temporary islands. Stars illuminate them, then fade. Black holes inherit the darkness, then may also disappear. Far beyond every familiar scale of time, the cosmos approaches a state that no observer may remain to witness. Yet the uncertainty is not emptiness. It is a boundary around knowledge, marked by measurements, theories, and unanswered questions. The beginning gives rise to matter, structure, and light. The future slowly separates them, leaving the universe to continue beyond the last star, beyond the last galaxy visible from any local shore, and perhaps beyond every process that gives time a recognizable rhythm.